This is a good summary of quantum mechanics.
What do you know about quantum mechanics?
I have a grasp on the basics.
Then you're doing it wrong. Is light made up of particles or waves? Quantum mechanics says it's both. How can it be both?
It can't.
It can't. But it is. It's paradoxical, and yet it works.
Okay, what do you mean this is... What do you mean? Yet it works. I don't understand.
Well, that's exactly right. So in quantum mechanics, we treat things statistically. You don't know that the roll of duct tape is in the shoebox or not. You just have to say, well, there's some probability it is, some probability it isn't. I've seen it here around the apartment sometimes. I've also seen it sometimes in the box. You treat things probabilistically. One of the consequences of this is that's a good example. Schrodinger's duct tape. I don't know if the duct tape is there unless I check it. I've collapsed the wave function. Hey, you're laughing, but I'm saying so that's right. Okay. So one of the consequences of quantum mechanics is that we treat light as a particle and also a wave, which is contradictory. Is it a wave or is it a particle? Is it an actual physical object or is it some conglomeration of effects that behaves like an ocean wave? Like the ocean wave isn't real. It's the water that's moving around that makes the ocean wave. And so we treat light like it's both, which is a paradox. It shouldn't be both. But it works. Like the math works, the descriptions work, it explains the experiments correctly. And so quantum mechanics is weird stuff. Like it shouldn't work, but the math is right. Like and the experiment verifies it. So here's really this idea which actually apparently is very old. I didn't know this, that in the 17th century, so that's 1600s. So it was Hooke from Hooke's law and Huygens from Huygens law. Huygens. He does astronomy, I think, versus Isaac Newton. So these two wanted waves. That makes sense. And then Newton wanted corpuscular light, so particle light. And so this ideas of should light be a particle, should be a wave. We're not sure. We need to do some further investigations. It started all the way in the 17th century, the 1600s at the tail end. Okay, and then in quantum mechanics then dives in and is able to explain that it really should be both. And so here, this is Young's double slit experiment. It's if you shine light from the left during the right, going in a plane wave, just a nice flat lines. From a single slit, you get light spreading out. Whereas if it was a particle, you should have gotten a dot right in the middle. But if you get light spreading out, and then you go into a second slit, you have that same effect again, but from now these new origin points. And if you look at a wall some distance d away, you get this pattern of bright, dark, bright, dark, bright, dark. And so if you had particle light, so I guess like corpuscular light, particulate light, then you should get a bright dot right here, right in the middle, bright dot right here in the middle. But instead you have these interference patterns, which is accurately described as waves. This is the same idea as when you're at a dock and if for whatever reason they have, I guess you could have a pole here or something. You get these waves spreading out. I mean, try splashing water in a pool. You get these waves splashing out. And so if this experiment suits the description of light behaving like a wave, then that's what it is. But at the same time, there's the photoelectric effect that Einstein did this experiment. And this supports a particle-like description. Actually, you're better explaining this one than me. Can you explain this for us?
Oh my gosh, here we go. Okay, so shine light on the surface of metal.
Okay.
And that can make electrons pop out of the metal. And those electrons can be detected elsewhere as a current or voltage, depending on how you want to do it. Let's say a current. So you shine light on a surface, electrons pop out of the surface, and you can measure a current of the electrons coming out. Mm-hmm. And Einstein's experiment found that if you shine light on a surface, you can dial in you can turn up the brightness or turn down the brightness, and that doesn't determine if current flows. The thing that determines if current flows is the wavelength only.
Oh.
So if the wavelength has too low of energy, no matter how bright it is, I will never get a current. Electrons will never pop off the surface. Which means I can't continuously change the intensity of the light, or when the electron absorbs the light, it only absorbs it in packets of particular frequencies, which means it's somehow coming in packets, which is particle-like.
I see.
Yeah, go ahead.
If I can rephrase this, what you're saying is the color of light doesn't matter. So if I were to use low energy light, like red light, I would never get electrons to pop off, even if I made the light
Exactly.
super bright. I would
Yep.
have to change the light to purple or ultraviolet or something, and then the electrons would pop. And then also you said another part of that is if I make the light really bright, if it was a wave, the electrons could like collect light, get energized, and then pop. Like,
Yep.
but the data showed never unless you change the color of light.
That's right. And since the color of light is determines the energy of the light, and if it comes in packets and is absorbed in packets, then you will only see a current when the wavelength has enough energy, meaning each packet of light has enough energy, which means it's coming in packets.
That's a particle.
That's a particle. That's super weird.
And so quantum mechanics meshes both of these. It's got to be a wave. It's also got to be a particle. And so the math somehow works for both. But we don't worry about if it's a particle or a wave. We switch, pretend, depending on what works.
Yeah, I don't know if has quantum mechanics actually figured out this, or is it just like, it's weird. Calculate. Has it
Okay.
figured out, like when I learned quantum mechanics, it was really like it's both a particle and a wave. Done. Now be quiet about that.
Yep.
Let's just start calculating.
Yeah. Yeah. It's like if you are drunk with people that you trust, you're like, do we really know this? You're like, nah, not really. Like sometimes it's a particle, but then if you're like in public, you're like, sometimes it's a particle, sometimes it's a wave. Don't worry about it. It's paradoxical. That's right. Don't worry about it. The math works.
Yeah.
That's true.
Yeah. Which gets back to, hey, it doesn't make sense sometimes, but hey, it works.
It works. Yep.
So weird.